Okay to start?
Yep, whenever you're ready.
Okay. Okay, so here I'm going to be working through some problems in what I call problem set A. The first problem states that using the Henderson-Hasselbalch equation, explain why when a solution is at a pH below the pKa for an acid, that more than 50% of the molecules have the proton on and not off. Well, let's think about this. So the Henderson-Hasselbalch equation, of course, says that pH is equal to the pKa plus the log of the salt, which I'll abbreviate as A minus, over the acid, which I'll abbreviate as HA. And so it says that in this case the pH is below the pKa, meaning that the pH is less than the pKa value. All right? Well, what does that mean? That means, let's say, as an example, that the pH were 2 and the pKa were 3. Doesn't matter what the actual numbers are. The most important thing is that this pKa value is greater than the pH. Well, if I have a pKa value that is greater than the pH, when I take it to the other side, what am I going to get? I'm going to get a negative number. And a negative number then is equal to the log of A minus all over HA. Well, to get rid of that log term, of course, I take 10 to that power, so I take 10 to a negative power, and that's equal to A minus all over HA. What does that mean? Well, 10 to a negative power is some fraction of a number. Remember, first of all, that 10 to a positive power is going to be a number greater than 1. 10 to a negative power is going to be a number less than 1. 10 to 0, of course, is going to be equal to 1. So 10 to a negative power means that this ratio is going to be less than 1. Well, if this ratio is less than 1, that means that we must have more HA than we have A minus. And we've solved the problem. The second problem says, using the Henderson-Hasselbalch equation, determine the ratio of salt to acid present in a 1 molar solution of a weak acid with a pKa of 3 at the following pHs. So let's remind ourselves first the Henderson-Hasselbalch equation, pH equals pKa plus the log of the salt all over the acid. This problem tells me that the pKa for this acid is 3, and I want to know what the ratio of salt to acid is at the following pHs. Well, the first pH I get is 1, and so 1 equals 3 plus the log of A minus all over HA. And when I do that, I get minus 2 equals the log of A minus all over HA. And we can see again that we've got a minus sign. And so to get rid of the log term, we take 10 to that power. And that negative sign here is going to tell us that this ratio is less than 1, meaning there's more HA than there is A minus. Now, you're not going to be required to use a calculator to solve problems like this, but I'm just showing you and stepping through here so that you can see how these ratios change as the pH changes relative to the pKa. If I plug this into a calculator, what I see is that 0.01 equals A minus all over HA, meaning that I have 100 times as much HA as I do A minus. If I go through now and I change the numbers so that instead of a pH of 1, I have a pH of 2, okay? Now I get minus 1 here, I get 10 to the minus 1, and now I see that this is equal to 0.1 is equal to the ratio of A minus over HA. I see that the ratio now has gone from, in the first case, 0.01 to 0.1, meaning that the relative amount of A minus has actually increased, but it's still less than the overall amount of HA. In this case, it's 1 to 10. I see 1 molecule of the A minus for 10 of every HA. When I get to a pH of 3, I see something interesting that happens, and at a pH of 3, the pH equals the pKa. So when that happens, I get 0. I now say 10 to the 0 is equal to A minus over HA, and that means that that ratio is 1. So when the pH equals the pKa. The quantity or the concentration of A minus equals the concentration of the HA. And that's one of the guiding principles of the Henderson-Hasselbalch equation. Plugging in the other numbers, we can see how this ratio continues to change. If we, for example, say have a pH of 5 is equal to this, then when I bring the 3 over, I say that 2 is equal to that, or that 10 to the second power is equal to that. In this case, I have a ratio of A minus to HA of 100 to 1. Now I have a lot more A minus than I have HA, and so when the pH is above the pKa, I'm going to have more A minus than HA. When the pH is below the pKa, I'm going to have more HA than I'm going to have A minus. In this case, we're off by 2 pH units, and that gives us 100 to 1 of the salt to the acid. Well, as I increase the pH, not surprisingly, that ratio will continue to increase, as we can see. So, for example, if I plug in a pH of 7, I see that 4 is equal to this, 10 to the 4th is equal to the ratio. This equals a ratio of 10,000 to 1. Okay? So the further that pH goes above the pKa, the greater and greater this ratio gets, in this case, in the favor of the salt. And if I then go to the last pH in the problem and take a look at it, I have a pH of 9, okay? And 9, that gives us 6 here. 10 to the 6th equals the ratio of the salt to the acid, and that would correspond to a ratio of 1,000,000 to 1, salt to acid. So the further the pH value is away from the pKa, the greater the ratio will be in terms of A minus over HA if this is a positive number, and the greater the ratio will be in terms of HA compared to A minus if this is a negative number. Problem number 3 says that formic acid has a pKa of 3.75. And acetic acid has a pKa, so this is formic acid, which I'll call HFA, and acetic acid, which I'll call HAC, has a pKa of 4.76. Why do we consider formic acid to be a stronger acid than acetic acid? And it says your answer must have a mathematical basis. Well, let's imagine a situation that we have both of these acids, and we'll pick a pH and compare the ratios between the two. So to make it simple, let's do the following. Let's say that we have both acids, and they're both present at a pH of, let's say, 3.75. So 3.75 turns out to be convenient. So let's consider the situation first where we have the HFA. When we have HFA, we say that the pH 3.75 is equal to the pKa 3.75 plus the log of the salt over the acid. When I do that, I get 0 is equal to the log of the salt over the acid, or 10 to the 0 is equal to the salt over the acid, which means that 1 is equal to salt over acid. It means I have equal concentrations of salt and acid. Okay? If I, by contrast, look at HAC, at the same pH now, this is important, at the same pH, what's the ratio of salt to acid? Well, at 3.75, is equal to the pKa for acetic acid, which is 4.76, plus the log of salt all over acid. We take that to this side, we get minus 1.01 equals the log. Is that right? Yeah. Is the log of salt over acid. So that 10 to the minus 1.01 is equal to salt over acid. Here the ratio of salt to acid was 1 to 1. Here, if I do these numbers, I will see that this is equal to 0.1 equals salt over acid. Now, what does that mean? It means that at the same pH of 3.75 and 3.75, the salt, there was equal amounts of salt and acid here. There was a lot less salt than there was acid here. Well, how do we get salt? We get salt by the dissociation of acid, meaning that there was less dissociation at this pH for acetic acid than there was at this pH for formic acid. Well, a strong acid is something that dissociates more. So, of course, this acid has dissociated more at the same pH compared to acetic acid, and consequently, it's for this reason we say that formic acid with the lower pKa value is a stronger acid than acetic acid, which has the higher pKa value. Problem 4 says that a new molecule is discovered called blemium. It contains ionizable groups with the following pKa values. So it has a carboxyl, and I'll call this number 1, with a pKa value of 2.2. Okay, has carboxyl number 2 with a pKa value of 4.4, an amine, which I'm going to label as NH, just as an NH group, with a pKa value of 5.0, an amine with a pKa value of 8.5, and an amine, this is number 1, number 2, and amine number 3, with a pKa value of 9.5. And it says, predict the charge on blemium at the following pH values: 1, 7, and 11. Well, to do this, I like to just draw some representation of this molecule. So let's do that. Let's say that we've got, and we can make up anything we want, just so long as we include all of these individuals here. So let's put in, for example, a COOH. We'll call this one number 1. Put in another COOH. We'll call this one number 2. And then we've got 3 amines. So we're going to put in H number 1, and H number 2, and finally NH number 3. Okay? Well, to determine the charge on this guy, all we have to do is apply the rule that I gave in class about whether the pH is 1 or more units above the pKa or 1 or more units below the pKa to determine if the protons were on. Well, the rule says that if the pH is less than the pKa by more than 1 unit, then the proton is on. And if the pH is greater than the pKa by more than 1 unit, 1 or more units, then the proton is off. Well, if we apply that rule to each of the groups that we see here, we can determine the charge overall in this molecule. So let's start, for example, in the middle. Let's start with pH 7. So at pH 7, what do we see? Well, we compare the pH to the pKa value and ask, is the proton on or is the proton off? Well, in this case, pH 7 is more than 1 unit above the pKa value of this carboxyl number 1, means the proton is off. So we take this proton off, and we take a proton off a carboxyl group, we end up with a negative charge. And you can see that negative charge right there. Carboxyl group number 2 has a pKa value of 4.4, but 7 is also above 4.4, and that means that this proton is also off, leading us to a negative charge. All right, now if we go to the first of the amine groups, we see that it has a pKa value of 5, and the pH is 7. So again, the pH is more than 1 unit above the pKa. That means that the proton is on. Well, for an amine, the proton is off. For an amine, that means that we have an NH2, and it means that the charge in that NH2 is 0. On the other hand, if we look at amine group number 2, we see that the pH is more than 1 unit below the pKa value, meaning that the proton is on. Oh, I got the wrong one here. Blasted. Total confusion. Okay, there's number 1. Sorry about that. Okay, if we look at at amine group number 2, we see the proton is on because the pH is more than 1 unit below the pKa value. When we have a proton on an amine, we have a 3 there, and we have a plus charge. If we then look at amine group number 3, we see the pH is more than 1 unit below the pKa value, meaning the proton is on. Again, we have a 3 for that, and we have a +1 charge. Well, if we add up the charges, what do we see? A -1, a -1, a +1, and a +1. At pH 7, the overall charge for this molecule is 0. Well, what if we look at the same molecule at pH 1? What happens? Well, at pH 1, 1 is more than 1 unit below the pKa of the first carboxyl, meaning that the proton is on, and a COOH gives a charge of 0. Okay? The second carboxyl group right here, the pH is 1, more than 1 unit below the pKa value, means that that proton is on, and we also have a charge here of 0. If we look at the first amine group, pH is more than 1 unit below the pKa value. The first amine group will have the proton on, meaning we'll have an NH3, and we'll have a plus charge. Well, similarly, amine group number 2 has the proton on, amine group number 3 has the proton on because they both have Ka values greater than the pH, so the pH is more than 1 unit below the pKa, and that leaves them with an NH3 plus and an NH3 plus as we see here. The overall charge of the molecule at pH 1 will be 0 plus 0 plus 1 plus 1 plus 1. At pH 1, the overall charge of this molecule will be +3. Last, if we look at pH 11, we can decide the charge of the molecule. So at pH 11, the pH is more than 1 unit above the pKa value for carboxyl number 1, meaning that proton is off, and we have a charge of 0. Similarly, carboxyl group number 2, pH is more than 1 unit above the pKa, the proton is off, and we have a charge of -1 again. That's a minus there. Okay. In the case of the first amine, pH is more than 1 unit above the pKa value, meaning that instead of an NH3, we now have an NH2, and we have a charge of 0. Amine group number 2, the pH is more than 1 unit above the pKa, so instead of having an NH3 plus, I have an NH2 0. And last, amine group number 3, the pH is more than 1 unit above the pKa value, and so instead of having an NH3 plus, I have an NH2 with a value of 0. The overall charge of this molecule is minus, minus, 0, 0, 0, or an overall charge of -2.